And we have another figure. In this figure, this is the solid surface, this is the solid surface, and when we have a fluid flow, this is a more generalized figure, we have a fluid flow of magnitude u infinity, then near the surface we can have the concept of boundary layer, which is shown here with the help of this line, and we have selected control volume in such a manner so that 1, 2 lies outside the boundary layer, 1, 2, 3, 4. So we can write the continuity equation, we can write the momentum equation for this given control volume 1, 2, 3, 4. We can find out this tau w and we can generalize it, and we can give the answer that what is the total shear resistance offered by this surface, or by the fluid on the surface and by the surface on the fluid, both way, right. So basically this is the concept given by von Karmans, and von Karmans did not use the NS equation, he used the concept of control volume for giving the answer that what is the force offered by plate on the fluid or by the fluid on the plate. So basically we can write continuity equation and we can write momentum equation. Here we have continuity equation. What is the mass flow rate going inside the control volume through phase 1? What is the mass flow rate going inside the control volume through phase this 1, 4? If velocity at this point is u, then u multiplied by rho multiplied by area, area is dy, and in the plane perpendicular to this figure, if thickness is taken as unity, then what is area? Dy into unity, dy into 1 multiplied by rho into u. This will be the mass flow rate going inside the control volume through this strip of thickness dy. If we want to calculate for 1 to 4, where 4 is lying on the surface, we have to integrate because u is a variable. This u is a variable. U is a variable. Outside the boundary layer, this u becomes capital U and it is constant. So this is 0 to L. It may be 0 to infinity, basically it can be taken as 0 to infinity, but it can be reduced to 0 to L, 0 to delta, because outside the boundary layer, what is u? This u becomes capital U, right. So let us don't consider this case here, keep it as 0 to infinity or 0 to L, since we are solving for the control volume of have length L in perpendicular direction. So 0 to L rho u dy. This is the mass flow rate going inside the control volume through phase 1, 4. Similarly, we can find out what is the mass flow rate going outside the control volume through phase 2, 3 with the same approach, but we have to use the concept of Taylor's expansion series. So with the help of Taylor's series, we can write that what is the mass flow rate going outside the control volume through that right phase. This is the mass flow rate going outside the control volume, this is the mass flow rate going inside the control volume through phase 1, 4 it is going in, through phase 2, 3 it is going out, because we have a velocity in x direction. If there is more mass going out from 2, 3 than 1, 4, then naturally some of the mass is coming from 1, 2, because no mass can enter through 3, 4, because 3, 4 is in the within the solid boundary. So from the solid boundary, no mass can enter into this control volume. And since flow is a steady flow, so it means that inside the control volume, rate of change of density or rate of change of mass must be 0. So it means that whatever mass going outside the control volume through phase 2, 3 must be coming from 1, 4 and 1, 2. Right. With the help of this concept, we can write the continuity equation. Similarly, we can write the momentum equation. In momentum equation, What is the momentum going inside the control volume through phase 1 4? It is rho u multiplied by dy into area. This is the mass flow rate. Mass flow rate, momentum is equal to mass into velocity. So rho u dy into 1 into u. So it is rho u square dy. This is rho u into dy into u. So rho u square dy integral. And what is the momentum going outside the control volume through phase 2 3? It is, with the help of Taylor's expansion series, can be written in this manner, right. So this is about the mass flow rate, this is about the momentum exchange. We have studied this thing in great detail, that how to write continuity equation, how to write momentum equation for control volume with the help of Reynolds transport theorem. So we can now write the momentum equation. What is momentum equation? Momentum equation states that force in x direction is equal to rate of change of momentum of the control volume, which is 0 because flow is steady flow, plus momentum going outside the control volume minus momentum going inside the control volume in that direction, if we are talking about x direction, right. So what is the momentum going outside the control volume in x direction, and what is the momentum going inside the control volume in x direction? With the help of that concept we can write the momentum equation. And what is the force acting in x direction? Since 1 2 is lying outside the boundary layer, so it is not subjected to any shear stress, because outside the boundary layer shear stress is 0. We are not assuming that fluid is having any viscosity. Fluid may be treated as inviscid flow, or flow is a rotational flow. If flow is a rotational flow, then 1 or 2 is not phase 1 2 is not subjected to any shear resistance. So here force is 0 because of shear resistance. And what is the force here because of the shear stress? It is tau w. And what are the forces acting on 1 4 and 2 3? Since we have a pressure force acting on 1 4 and pressure force acting on 2 3, so it will have component in x direction. So here pressure is equal to P on the left hand side, and on the right hand side with the help of Taylor's expansion series it is P plus del P over del x into delta x, because del P over del x is gradient in x direction multiplied by delta x by neglecting higher order term. So with the help of, and what is the direction of the pressure? Pressure always acts on the control volume in such a manner so that it compresses the fluid. So this one is acting in this direction and this pressure force is acting in this direction, right. So we have these two kind of pressure forces. As far as the weight is concerned, since weight is acting in a downward, we are not interested in a downward force, we are interested only in x direction force in a horizontal direction or direction of the flow. So that's why we are not considering the weight component. So we have a pressure force on this side, pressure force on this side, and shear stress on this side. So these are the three forces. With the help of these three forces we can write the left hand side of the momentum equation, and with the help of momentum going outside the control volume minus momentum going inside the control volume in x direction we can write the momentum equation.